Most people think of the Arctic as a sterile, lifeless place. Extreme cold, 24-hour sunlight, or months of darkness. It's difficult to believe anything could survive here for long. But if we look on a microscopic scale, we see within the frozen landscape there's an abundance of life. Although hundreds of miles from where most people choose to live, these organisms have huge significance for everyone on Earth. Playing a key role in the melting of our largest glaciers and ice sheets, affecting global weather systems, and diverting ocean currents thousands of miles long. These microscopic organisms could even teach us about the potential for life elsewhere in our solar system. With millions of people at risk from the effects of climate change, we need to know more about this life.
There's a lovely adage that ignorance is bliss. But in an increasingly complex world, knowledge may be your only means for survival, and ignorance no longer becomes blissful. I think our collective understanding of the Arctic is so shallow and so almost inconsequential that any way that we could broaden that and deepen that and make people see the Arctic for what it truly is going to be beneficial for the planet itself.
At a time when our planet is warming, greater numbers of scientists are traveling to the Arctic for their research.
If you think about life in the Arctic, you probably think polar bears, you might think narwhals or certain types of birds and those kinds of animals. I'm interested in what actually lives on the surface of our glaciers and ice sheets. And that's a microbial ecosystem. We live in a world that is getting warmer, and that means that glaciers and ice sheets are melting. It's more important than ever to understand that actually these tiny microbes are causing glaciers and ice sheets to melt faster.
Explorers have tried to draw public attention to the importance of life in these inhospitable regions as far back as the 1870s. Adolf Nordenskjöld noted that ice on his expeditions in Greenland was often brown, grey or black. After checking some samples under a microscope, he discovered traces of bacteria and algae. In a section of his diary, he wrote that life was the greatest enemy of the mass of ice. Scientists are only now beginning to realize the true significance of Nordenskjöld's discovery.
Greenland is the largest continuous mass of ice in the Northern Hemisphere. And it's a giant reflector for solar radiation. So in that way, it's kind of a cooler for the planet. Because the Greenland ice sheet's so big, when it melts, it pushes cold, fresh water into the ocean that can actually change the global circulation patterns within the oceans, which is important for weather elsewhere on the planet. Equally, it's a giant cold mass that changes the air circulation patterns above it. And dynamics of the Greenland ice sheet can actually push more extreme weather down into Northern Europe. This is such an unlikely place for biology to exist because it's really, really cold. There's very few nutrients, and because of the midnight sun here, they basically get fried by UV radiation all the time. But on the other hand, you've got sunlight to drive photosynthesis, and you've got liquid water and some nutrients. The Greenland ice sheet is actually somewhere where life thrives, somewhere fundamentally biological. Ultimately, this ice is alive.
To understand how life survives in this harsh environment, explorers have needed to brave the conditions themselves and look for evidence of it. To an experienced eye, it doesn't take long to find.
There's two main habitats on the ice surface. The first one is cryoconite. This is granules of biological activity. It's all bundled up and melts down into melt holes. These cryoconite holes look really simple. They look just like buckets with mud in them, not very inspiring. But there's actually a hidden level of complexity that I find absolutely fascinating.
It comes from the Greek word. Cryo is ice and conite is dust. So it's basically dust on ice. But this dust has both mineral and biological fragments. Because the debris is dark in color, it absorbs heat. And when it absorbs heat, it starts to melt the ice around it. And as it melts, the cryoconite or debris, it moves lower into the ice and creating this sort of cylindrical hole that we see.
From high above, the Greenland ice sheet appears to be a featureless wasteland. But often, the surface is riddled with thousands of holes like these. As we dive into a cryoconite hole itself, we begin to discover a complex habitat, which on a microscopic scale appears as a rocky mountain range. Looking closer still, this landscape is home to a rich ecosystem of organisms. Some of these organisms are capturing energy from the sun through photosynthesis, while others have moved in to feed on them.
There are different levels of communities that harbor cryoconite holes. Mostly we find autotrophic filamentous, so a lot of stringy cyanobacteria. We find a lot of heterobacteria, fungi, and ciliates. And if you move up higher on the trophic level, different heterotrophs, we have tardigrades, which are these 0.5 millimeter creatures. And then there are ice worms, midge larvae. So there's different levels of ecosystem that you can find in just, you'd think it's just a puddle of mud.
And these habitats are not isolated.
Now, these cryoconite holes are connected to one another by meltwater that's flowing through the ice between ice crystals just under the surface. And in that meltwater, there are cells and there's nutrients being transferred between these cryoconite holes all the time. There's a constant flux of materials in and out of each one. So they're better thought of as like little microcosms for cities. You've got a load of processes going on in there, just like we do in human cities. There's immigration and emigration of cells, there's production and consumption, there's construction, destruction, competition, birth, death, life, all kinds of hidden layers of complexity going on within this environment that looks so simple. The other habitat is actually on the ice surface itself, in a small, thin, liquid water film between the crystals right at the ice surface. And they're algae, ice algae. They're very dark because they produce carotenoid pigments and purpuragallin pigments, and they darken the algal blooms and therefore darken the ice. The colour of the ice is really important because the colour determines how much solar energy is absorbed compared to how much is reflected, and the amount absorbed controls how much energy is available to melt ice.
One of the emerging concepts of research within this field is bioalbedo, and this is the idea that biological forces influence the albedo of Earth's glaciers and ice sheets. And albedo is simply the reflectance of solar energy back into the atmosphere. So if something has a high albedo, it's reflecting most of the sun's energy back, so the surface can stay pretty cool. If, on the other hand, something has a low albedo, it's absorbing most of that solar energy and it becomes warmer.
It's the same thing as if you go out in a dark t-shirt on a warm day, you get warmer than if you go out in a white t-shirt.
In the context of ice, this is bad news. To have a low albedo means that solar energy is being pulled down into the ice and it's making it melt faster. So the ice algae are producing dark pigments related to the pigments that you find in black tea, and that's darkening the ice. The cryoconite are producing photosynthetic pigments by degrading chlorophyll and turning it into humic substances, much like you'd find in soil. So you have this combination of the ice algae with their tea darkening effect, and then the cryoconite with its proto-soil formation on the ice surface, both having a bioalbedo effect, darkening the ice, making it melt faster, and ultimately that meltwater is going to contribute to sea level rise. As microbes hasten the melting of ice, this is a positive feedback. So the more melt you generate, the microbes can feed off nutrients that are released within the melt water, and you get more microbial growth. So there's a vicious circle of microbial growth and melt driving each other on.
As we have warmer, longer summers, that means we have a longer growth season for these algal blooms. That means we get more growth over the course of the season, which results in more darkening and therefore more melting.
So the biological processes are very closely driving positive feedbacks in ice melt, and that's the scary thing, because current projections of how glaciers and ice sheets respond to climatic warming don't include this biological albedo feedback.
As our understanding of microbial life in the Arctic develops, work needs to be done to measure the precise scale of the problem.
So this is an instrument for measuring the reflectivity or the albedo of the ice surface. And this is a tripod that just keeps everything flat and level. That means we can be away from it and not cast a shadow. And on the end here, we've got an optic called a cosine collector. And what that does is gathers all of the reflected light from the entire hemisphere. So all the angles, 180 degrees and 360 degrees around. So it's not biased in any one particular direction. And what we do is we make a downwards looking measurement to get all the light that's reflected off the surface. And then we flip it upwards to get all the light that's coming down from above. And the ratio of one to the other is how much of the incoming light is reflected. What we're going to do with this is measure different types of ice, clean ice, dirty ice, ice with algal blooms, cryoconite holes. And then we're going to take ground samples as well. So we're actually going to take some of the ice back to the lab and find out what's in it. So we're going to look to actually measure what the albedo is and how many microorganisms there are and what type.
On an ice sheet roughly the size of Mexico, there's a limit to how much can be discovered on foot.
The problem with fieldwork is that you can really only go to one place, and you stay there for maybe a month, and then you get picked up and you have to go home again. So you can't keep moving around to understand what's going on at different places.
This image, taken 700 kilometers from the Earth's surface by NASA's Terra satellite, shows the western edge of Greenland's ice sheet during winter. In the summer months, as the melt begins, a vast expanse of ice darkens. It's only at this scale that we can understand the size of the task facing polar scientists.
What we're trying to do is we're trying to use our field measurements from one site to help understand what's going on at an ice sheet wide scale by looking at satellite imagery of the colour or the albedo of the ice sheet. And also we're trying to improve models that simulate the melting that the surface of the ice sheet undergoes each summer.
One way to cover more ground is to take to the skies.
The idea with the drone is that it links ground measurements to what we can see from space. So we're going to fly that with a very specific camera on the front, and that camera can actually pick up different wavelengths of light reflected off the surface, and we can use those different wavelengths of light to identify different contaminants, one of which is life. The drone effectively adds a dimension to what we're doing. It's not just a point on the ground anymore. We can fly back and forth over a grid on the ice sheet and create pictures in different wavelengths of light that show where life is. And using the same algorithms, using the same wavelengths of light, we can then ultimately do that from space, because there's satellites already going around the Earth that measure those same wavelengths of light.
The Earth is just another living, breathing, vital body that we don't really completely understand. If we stay up close, we can get certain amounts of data, but to be able to go around the whole world in a couple hours, to measure things not just in one localized area, but to say, let's measure all of the ice on Earth and see how the volume of ice on Earth is changing from week to week and year to year. Then we can start to draw global conclusions. And hopefully with that, then start to think about, oh, well, these are actions that will not just affect us locally, but that will have a global impact.
The data collected by scientists is helping to improve our knowledge of the rapidly changing conditions in the Arctic. To properly tackle the effects of man-made climate change, accurate predictions that include all of the factors affecting the melting of ice and snow need to be made. The challenge is to achieve that on a global scale. And the potential for this type of technology isn't limited to our planet.
Ultimately, we can potentially turn those sensors around and stop looking back at our own planet and start looking at other ice in our solar system. For example, Europa or Enceladus are ice surfaces where there's the potential for life. And the same technologies that we're using to detect life on the Greenland ice sheet, maybe they're applicable to finding life elsewhere in the universe.
But surely, before we look too far into other worlds, we must first deal with the problems facing us here, on Earth.
With 7.5 billion of us on the surface, we are a globally dominant species. We can't just pretend we only have a local effect anymore. And so with the success of our species comes the responsibility of thinking of stewardship at a global level. And the only way to properly do that is to gather information worldwide.
The scientific question around climate change isn't, is it happening? The scientific question is now focused on the details. It's how fast is it happening, how long have we got to act, and how should we act? And one of the key things that's going to determine how we act and when is understanding precisely how glaciers and ice sheets melt. And understanding the actual process is going to be key in predicting ice retreat, deglaciation, and the knock-on effects for Earth's climate.